This movie deals with centripetal force. It is intended for viewing before students do a laboratory experiment designed to illustrate how centripetal force is determined using a photo gate detector. Upon completion of the laboratory activity associated with this movie, students will be expected to be able to determine the velocity and acceleration of an object moving along a circular path at constant speed, and define and contrast centripetal and centrifugal force. Suppose an object is moving at constant speed along a circular path of radius r. How can we measure its speed? The circumference of a circle is equal to 2 times pi times the radius. Therefore, when an object completes one revolution, we can say that it has traveled a distance equal to 2 times pi times r. Speed is just the distance traveled divided by the elapsed time. So if we define tau as the time elapsed as the object completes one revolution, we can get the speed by taking the distance traveled, 2 pi r, and dividing it by tau. By rearranging this equation, it is easy to show that the tau is equal to 2 pi r divided by the speed, v. If the motion of an object repeats itself over and over, then we say that its motion is periodic. The time it takes for each cycle to complete is called the period. In the case we have here, the motion is periodic if the object goes through several revolutions at constant speed, and one cycle involves one complete revolution. For an object moving in a circle, the radius r is constant. We can show that its speed is constant by showing that its period is constant. This is what we will do in this experiment. We will measure the period for several revolutions and show that it is constant. From the average period, we can calculate the speed of the object. A quantity often used to describe periodic circular motion is frequency. Frequency is the reciprocal of the period and is simply the number of cycles completed per unit time. It is somewhat easier to visualize the motion given the frequency, especially at high speeds. For example, a period of 2.0 times 10 to the negative 4 seconds corresponds to a frequency of 500 revolutions per second. Note that we can calculate the speed directly from frequency. The speed is equal to the distance traveled per revolution, which is 2 pi r times the number of revolutions per unit time, f. Consider the following problem. A ball tied to a string of length 5 centimeters is spun at a rate of 50 revolutions per minute. What is the speed of the ball? The distance traveled by the ball per revolution is the circumference of the circular path. It's equal to 2 times pi times the radius of the circular path, which in this case is 5 centimeters. This gives us a circumference of 31.42 centimeters. The time it takes for the ball to complete one revolution is simply the reciprocal of the frequency. 1 divided by 50 revolutions per minute equals 0.02 minutes. That is 1/50th of a minute. The speed is equal to the circumference 2 pi r divided by the period, 2 pi r over tau, r, the circumference multiplied by the frequency, 2 pi r f. Plugging in the radius and period, or frequency, gives us a speed of 1.57 times 10 to the third centimeters per minute. Consider the object represented here by a yellow square. Imagine the object is moving with speed v in the direction indicated by the blue arrow. According to Newton's first law, the object will continue to move at constant speed in this direction unless there is a net non-zero force acting on it. Suppose you want the object to follow a circular path instead. What would you have to do? You will try to push or pull so that it would veer downward instead of going straight to the left. You will need to exert a net downward force on it. In fact, if you wanted to continue following the circular path, you will need to continuously exert a force that is directed toward the center of the circle, regardless of where the particle is on the circle. The velocity vector is always tangent to the circle, and you will need a force directed toward the center of the circle to keep changing its direction. Since the force is directed toward the center, we call it centripetal force. Centripetal means center-seeking. Newton's second law says that force equals mass times acceleration. The acceleration vector points in the same direction as the net force on the object. In this case, the acceleration is also directed toward the center of the circle. It can be shown that for an object moving at constant speed, v, along the circular path of radius r, the acceleration is equal to v squared divided by r. r, in terms of frequency, it is equal to 4 pi squared times frequency squared times r. The derivation can be found in just about any standard physics textbook. The centripetal force is simply equal to the mass, m, times the acceleration. One comment before we move on. You may have encountered the term centrifugal force. You will recall that Newton's third law of motions says that for every action there is an equal and opposite reaction. The centrifugal force is the reaction force for centripetal force. It is directed outward, but it is not acting on the object. This is the force exerted by the object on whatever is pushing or pulling it inward. Let's calculate the acceleration and mass of a ball on a string of length 5 centimeters being spun at 50 revolutions per minute. We have previously calculated its speed to be 1.57 times 10 to the third centimeters per minute. In meters per second, the speed is 942. The centripetal acceleration is v squared divided by the radius of the circular path, or 4 pi squared times the radius times the square of the frequency. This gives us an acceleration of 1.7 times 10 to the 7th meters per second squared. To calculate the centripetal force, we need to multiply the acceleration by the mass. Let's assume the ball has a mass of 2 grams. Plugging in the mass in kilograms and the acceleration in meters per second gives us a centripetal force of 3.55 times 10 to the 4th newtons. The goal of the first part of the experiment is to determine the period of a rotating mass for the photogate detector. The rotating mass is part of the centripetal force apparatus, shown here on the left. Here's the rotating mass. It is attached to a spring whose tension can be adjusted by turning the threaded collar on the other end of the spring. For this experiment, set the spring tension to a minimum by aligning the right edge of the collar to the 0 mark. The mass of the cylinder is engraved on the cylinder. Be sure to record it. The entire apparatus will be rotating using a variable speed motor. The axis of rotation is indicated by a pin in the middle of the apparatus. An opaque piece of plastic about 20 centimeters long and 2 centimeters wide is taped to one end of the centripetal force apparatus. Set up the apparatus so that, as it is rotated, the opaque piece of plastic passes through the photogate detector, once for every revolution. The electrical signal from the photogate detector, which is monitored by a computer, changes every time the opaque piece of plastic passes through it. That is, once per revolution. Time between these changes is determined as the period of the revolution. When the centripetal force apparatus rotates, you will notice that the spring stretches out as you increase the speed of the rotation. Adjust the speed of the rotation until the pointer is aligned with the tip of the center pin and the axis of rotation. You will note that the pointer tips as the spring is stretched. In both parts of this experiment, we want the spring to be stretched out by the same amount. We ensure that this is the case by making sure that the pointer is aligned with the tip of the center pin. You will use the PhotoGate timing program from Veneer software to collect data for this experiment. The program we have in the laboratory is an old one, but it runs in an MS-DOS box from Windows. The program is menu driven. It gives you a menu of what you can do as shown here. You select from the menu by pressing the up or down arrow keys on your keyboard until your choice is highlighted. Then press the enter key. Alternatively, you can simply press the letter corresponding to your choice. On the main menu shown here, for example, you press T to access the miscellaneous timing modes, S to check if the PhotoGate is working, and Q to quit. Before you start rotating the Centripetal Force apparatus, first make sure that the detector is working properly and is communicating with the PhotoGate timer program. At the main menu of the PhotoGate timing program, press S to check the status of the PhotoGate. It should say that the detector is unblocked. Wave your hand between the J-shaped bracket. As you pass your hand through the detector, the status shown on the screen should change to blocked. If your PhotoGate is not working, ask your instructor for assistance. Otherwise, press Enter to return to the main menu screen. With the Centripetal Force apparatus rotating at the appropriate speed, you can measure the period by selecting the following sequence of menu options in the PhotoGate timing program. At the main menu, press T to select miscellaneous timing modes. Then press P to select the pendulum timer. The program records the intervals between the times when the detector is blocked. Since it assumes it is collecting data for a pendulum, which will block the PhotoGate twice every cycle, the period it will report is twice the actual period of your Centripetal Force apparatus. Press L to select normal time display. At this point, the computer will start measuring the period. On your screen, you should see the number of cycles recorded and the period for the last cycle. Press Enter to stop the measurement after 20 cycles. Press to display the table of the data. Remember that the times reported are actually the times for 2 revolutions. You have to divide these by 2 to get the correct period. Copy the data. The program gives you other options for automated data analysis, but we will not use them. You will record your data in an Excel spreadsheet for analysis. Calculate the average period of the rotating cylinder in Part 1. The reciprocal of the period is equal to the frequency of the rotation. The speed can be calculated from the frequency and the radius of the circular path. You measure the radius in Part 2. This is the distance from the axis of rotation, that is, the center pin, to the engraved line in the middle of the cylinder. From the speed and the radius, you can calculate the centripetal acceleration. Finally, you multiply the acceleration by the mass of the cylinder to get the centripetal force. Remember that the mass of the cylinder is engraved in the cylinder. The centripetal force that you calculate is the force that pulls the cylinder toward the center pin as it rotates in Part 1. In Part 2, you found the total mass needed to stretch the spring by the same amount as in Part 1. Multiplying this by the acceleration due to gravity gives you the weight. This should be equal in magnitude to the centripetal force that you determined from Part 1.